In this lecture, we're going to define differential forms. And we're going to do this in two steps. We're going to define them on Euclidean spaces. So what we're going to do is we're going to take U to be an open subset of Euclidean space, and we're going to define what are known as differential forms on U. And interestingly, there are different approaches to how one can define differential forms. One can say that there is a algebraic approach. This is, you can say, an algebraic approach. Where you basically define differential forms. I'll just write forms as a bunch of symbols with certain rules. And then there's another approach. I'm not even sure how to call it. Maybe you can give it, well, I don't want to give it a name, but I'm basically going to say that you can give meaning to those symbols. If that's not clear, it will become clear as the lecture progresses. So the way we're going to do it is we're going to follow an algebraic approach. We're going to have a bunch of symbols, and that's all what they're going to be. They're just going to be symbols. They will mean absolutely nothing. They will just be symbols, and they will satisfy certain rules. And for the time being, it would be very helpful to not ask the question why. Like, why are we doing it? We're just going to learn how to do it. And then after we learn how to do it, you will then see the value for what they actually do for you. But for the time being, I just want to focus on the rules. The other approach is the symbols that we're going to be using is they can be interpreted. But then the price to pay is you have to introduce even more math to interpret what those symbols mean. And in the end, it's not worth it. So this approach, it follows a book, a very well-known book. The book is called Differential Forms in Algebraic Topology, and it's by Bott and Tu. The theme of the book is very interesting. It is a book on algebraic topology, and it specifically focuses on manifolds. In fact, smooth manifolds. And when you have smooth manifolds, the way you work with smooth manifolds is by using these objects called differential forms that we want to define. And the approach that the authors take in the book is they just kind of completely forget about this, and they take a much more rapid development of differential forms. They just define them as a bunch of symbols with certain rules, and then from that point on, they're able to do algebraic topology through a differential form approach. And that's the approach that we're going to use. It's very, you can say, efficient. It's a very efficient way to do it. But differential forms will proceed in two steps. So in this lecture, we're going to define differential forms on Euclidean spaces. So these will be open subsets of Rn. And then in the next lecture, because we want to work with manifolds, and then in the next lecture, we'll define forms. So from this point on, I'll just say forms. We'll define forms on a smooth manifold. The idea is that a smooth manifold is, by definition, it's made out of charts. And those charts are defined on Euclidean spaces. So you bring everything back to Euclidean spaces, and this current lecture will be then used to define the follow-up lecture. But today we're just going to talk about Euclidean spaces. So let's begin with the definition. And I have to warn you, these definitions are going to be unmotivating. It's not going to be clear why we're doing it. But as the semester progresses, we can sort of go backwards, reverse engineer it, and then give the motivation afterwards. I think it's actually, for learning purposes, better to just learn what forms are and then reverse engineer everything and try to look for the motivation after you know how to use them. So here's our definition. So let U be an open set in Rn. Let's define C infinity U, and these are just going to be, this is the set of functions, real valued functions, that are smooth. That's what this infinity means. It means it's infinitely differentiable. So what do we mean by smooth? So smooth means that the partial derivatives of your function of f exist of arbitrary order. So for example, so order just means how many times you differentiate. So you have your function, maybe you differentiate it with respect to the third coordinate. That gives you a function. Whatever function you get can be differentiated with respect to the first coordinate. Then you can differentiate with respect to the third coordinate. Then you can differentiate with respect to the second coordinate. And you can do this as many times as you want. That's what we call it smooth. This is also the reason why you want the function to be defined on an open set, because if the function is defined on, let's say, a closed rectangle, and you pick a point on the corner or on the boundary, if you're talking about the derivative with respect to the first coordinate, you're kind of moving in that direction and you're leaving the domain, right? How do we calculate the derivative of the function in a direction? We take the point, we move in that direction by a small increment, we look at the difference, and then we consider the limit as we shrink that difference down to 0. The problem, of course, is you're leaving the domain of the function. But when it's an open set, you stay away from the boundary and you have room to move around and you stay within the domain. That's why this open requirement is being used. It is possible to extend the definition of being smooth to a more general set, but let's not go there. If we do not need it, then let's not even bother to go there at all. So this is what it means to be smooth. And you can observe, so then observe that C infinity U forms what is known as a commutative ring. So what do we mean by that? It basically means, I do not want to give the full definition of it, I just want to give the basics. It basically just means that if two functions belong to this set of smooth functions, then their sum is smooth, their product is smooth, like this. Negative f, the negative of a function is smooth, so the negative exists. However, you can also say there's an identity function, right? There's the 0 function. So here by 0, I mean the 0 function, not the number 0. It has a 0 function. So this is a function that is the identity for addition. And it has a function that's the identity for multiplication. This is the function that is the constant function, and it's equal to 1. Okay, so commutative ring, it's not a field. C infinity of U is not a field because if f is a smooth function, then 1 over f, right, its multiplicative inverse, is not necessarily defined on U, because it's conceivable this function vanishes at some points and then its inverse, its multiplicative inverse, will not exist. So this is what we call a commutative field. It's very similar to sort of like what you have with the real numbers, right? If two things are real numbers, then the sum is a real number, the product is a real number, there's a negative for every number, there's a 0 real number, a 1 real number. But with real numbers, you have this nice property that if you pick something among the real numbers, excluding 0, the only exception is 0, every real number has a multiplicative inverse. But that's not true for functions. You can have a function that's not the 0 function, so it vanishes at some points but not others, but its inverse will not be defined because at the points at which it vanishes, that's no longer in the domain of your function. So that's why we call it a commutative ring as opposed to a commutative field. So this is what we call, you can call this the ring of, you can call this the ring of smooth functions. You could say the commutative ring of smooth, people just usually say the ring of smooth functions. So if you want to be fancy. Okay, so let's just remove all of this. And now I'm going to define what is known as differential forms. Let U be an open set in Rn. We might as well assume it's not empty, otherwise there's not really much to do here. We define forms on U. So these are going to be forms. Whenever you see the word forms, it means differential forms. I just do not want to keep on writing and saying differential forms. So these are going to be just forms on U. So this is what it is by definition. So this is going to be the algebra. If you're not sure what an algebra is, I will remind you. This is going to be the algebra over smooth functions. You can also say with coefficients in the smooth functions. So this is the algebra over the ring of smooth functions generated by the symbols. And we're going to call the symbols dx1, dx2, dxn. So there's going to be n symbols. The amount of symbols that you have has to match the dimension of the Euclidean space. Okay, so this number is not arbitrary. It's based on the Euclidean space dimension. So it's generated by these symbols. And because these are symbols, it does not matter what you call them. You can call them like *1, *2, and so on. You can also call them D1, D2, and so on. But we typically call them D. We write a letter, and then we index that. The reason for why we do that will be explained in a moment. But of course, these are just symbolics. Sometimes we use different letters. Sometimes we use Y's instead of X's. But at the end of the day, it's just symbolic. So it's generated by the symbols. These symbols have absolutely no meaning. Okay, let's just. So these are nonsensical symbols. We do not give them any meaning, but we do define rules to how to work with them. And again, it is possible to give them meaning, but then you have to do even more math to give them meaning, and it's just not really worth it for us. Generated by the symbols with the rule satisfying the rules that if you do dxi and you have dxj and you multiply them together. So the way you multiply, so the multiplication symbol for forms is denoted by a wedge. In the Bot and 2 book, they do not even bother writing a wedge, but it's just up to you if you want to write it. And it's defined to be negative if you do it the other way around. Okay, so that's the way you define it. So what is an algebra? So an algebra is, let's just say what that is. So an algebra is similar to a vector space, except in a vector space, vectors can only be added but not multiplied. In an algebra, the vectors can also be multiplied together. So you can say an algebra is one step above a vector space. So we're saying that these symbolics can be multiplied together. Now, maybe to give you a very simple example of an algebra, Rx1 up to xn, this is the polynomial algebra over the real numbers generated by the symbols x1 to xn, satisfying the rules that if you take xi and you multiply it by xj, that's the same thing as xi multiplied by xj. So in the polynomial algebra, your symbols are commutative. So it's like a commutative algebra. Whereas when you're working with forms, this is an anti-commutative algebra. So why is this an algebra? Well, just to show you how a typical element looks like is you might have like x1 squared x3, and then you have a coefficient. So the coefficient is going to be a real number, and then you have maybe like a half x1 cubed, right? And this entire thing, that's an element of your algebra, of your polynomial algebra, because this is a symbol. It's like a vector. The vector can be multiplied by itself because it's an algebra. And you can then, this is like a vector and that's a vector, and you can add vectors together. So this entire thing, that's just an element of this polynomial algebra. And that's how this is going to look like. So just to show you a very simple example, so let me take this down and show you a very simple example of a form. So let's say we talk about forms on, let's say, R2. So we're going to have two symbolics, dx1, dx2. It's also customary that if you're talking about two, you might just call them dx and dy. Does not matter what you call them. And then an example of an element, it will go something like this. You would have, let's say, dx. You have dx. And then you have a smooth function. Maybe you call that like f1. And this f1, this coefficient, this is a smooth function defined on R2. Then you can have maybe dx wedge dy plus like f2. So you can multiply these together, and you can have another smooth function. It's a coefficient. The distinction here is in the polynomial algebra, these are real numbers, whereas in the forms algebra, let's call it the form algebra. In the form algebra, the differential form algebra, these are smooth functions. By the way, if you want to, you can replace this by negative f2 dy wedge dx, because that's the way we define this rule, that it's anti-commutative. So you can rewrite it the other way around. So this entire thing, that would be an element of the differential form algebra on R2. Right? That would just be an example, and it should be reminiscent of the polynomial algebra, but it's a little bit different. So here's just a very simple observation. So just observe that if you do dxi wedge dxi, if they appear twice, it has to be 0. So this is going to be, so this 0 is referring to the formal 0 object in the differential form algebra on an arbitrary open set U. The reason for this is because if you were to interchange these, it's supposed to be negative dxi wedge dxi. So it's supposed to be the same as it's negative, and therefore that's why it ends up being 0. Okay, so we have that. So the next thing that I want to show you is the dimension. Okay, so here's the next part. Here's the definition. We define omega k of U. These are going to be forms. So you usually do not say forms in U. You rather say forms on U, because the coefficients of differential forms are smooth functions. And you talk about functions not being in the open set. You talk about the functions being defined on an open set. So these are going to be forms on U whose degree is k. What do we mean by a degree? It's exactly how it works with polynomials. If you have x1, x2 squared, the degree would be 3. Because this has degree 1, this has degree 2, so together they have degree 3. If you have just like x1, the degree would be 1. If you just have a constant like 4, then you would say the degree is 0, because there is no symbolic. So with differential forms, it will just mean the same thing. It's just how many differentials are you using? So let me just give you some examples. So let's say we talk about let's say we talk about two forms. So these are called two forms on R4. Okay, so these would be two forms of degree 2 on R4. Well, because you're working on R4, you're going to have 4 differential symbols. And then an example of something that would be a 2 form is you can have dx1 wedge dx2, and then you have a coefficient function. Then you have a coefficient function over here. Then you have dx1 wedge dx3. You can have some coefficient function dx1 wedge dx4 plus dx 2 wedge dx3 plus dx2 wedge dx4 plus, and some coefficient function, dx3 wedge dx4. You can always write them in ascending order, because if it's not in ascending order, you can flip them with a negative sign. And these are just smooth functions, right? So there's this arbitrary smooth function over here. You just call it like f1, f2, and so on. So these are just your smooth coefficients. And all of these taken together, this would be a 2 form. So in a 2 form, all of the monomials, as you can call them, the monomials, the individual components that make them up, all of the monomials are of degree 2. So we will call that a 2 form. So what you see over here is that these form a basis for all of the 2 forms. Okay, so you can say, so this is what we would say. So sigma 2 of R4 is a, so you're not going to say a vector space, because you want to say, like, okay, this is what you want to say, is a vector space over, so over smooth functions on R4 of dimension 6. But vector spaces are usually preserved when you talk about fields. So the actual terminology here is, you would say it's a module, and you would not say, you would say a free module, because it has a basis. In general, modules are not free. Only vector spaces are free. So you would say it's a free module over this commutative ring, because this is not necessarily a field anymore. And you would just say, instead of dimension, you would say rank. So that's really what but you're basically saying the same thing. You're just using slightly different language. What's the significance of this number 6? Well, all it is, this is just 4 choose 2. Because you have 4 differential symbols and you're choosing 2 at a time. So 4 choose 2, that's why the rank is 6. So in general, if U is an open set in R4, then omega, so the K forms on U is a free module, basically vector space, not over the real numbers, but over the ring of smooth functions of rank. You would say, maybe instead of 4, I should have said n. You would say n choose k. By the way, if the k number exceeds n, then it would be of rank 0, right? So let me write it over here. So if k is greater than n, then the rank would be 0. And that should make sense, because K forms on U would just be, it would only consist of the 0 form and nothing else. You always include 0, so 0 is always included, because you could say something like okay, so let's say you have 4 differentials, okay, 3, 4. You could do dx1 wedge dx1, but when you do that, that gives you 0. So you always include 0, the formal 0, in every single one of these. So at the very smallest, this would just be like the set consisting of only the 0 form and nothing else. So then this would just be 0. It's not going to be the empty set. It would just be 0. Okay, so this is the simple observation that we have here. And the next thing that we want to move to is we want to move to this operator called the differential operator. Now we define the differential form operator D. The operator D is a linear map k forms on some open set to k plus 1 forms on the same open set. So it increases the dimension. And to define it, so maybe you can even indicate by a subscript. You can say something like d subscript k, that this is the kth operator d, but we usually just write d. So to define d, which is called the exterior derivative, we first define the exterior derivative from 0 forms to 1 forms. Now, what are 0 forms? So 0 forms, and we did not talk about this before, but you can probably guess what this is. In general, a k form, it consists of smooth functions on U, and you're choosing k differentials. So here you're choosing 0 differentials, but you're using smooth functions. So this is just, really all this is that this is smooth functions on U. That's what that is. If that's not clear, just look at a very simple example. Let's say we want 0 forms on R2. So we have 2 differentials that generate the algebra, dx and dy. If we have a 1 form, then we can take, let's say, dx, we pick a function, and then we take another function, dy. If we have a 2 form on R2, we would take dx and dy, and then we would have a function, a smooth function as a coefficient. But if you have a 0 form, you're choosing none of them. So you're just choosing a function, but you're not choosing any of these differentials. And so that's why it's just smooth functions. So 0 forms are just smooth functions. So you're going to define it from the 0 forms to the 1 forms. And this is the way you do it. So for f, a smooth function, df is then equal to, and this is by definition, this is what we do. We're going to take the derivative of f, the partial derivative of f, with respect to the first coordinate. Then we multiply it by dx1. Then we take the partial derivative of f with respect to the second coordinate. We multiply it by dx2, and so on. Then you have d nf dxn, where these d's, these ones over here, these are just symbolics, right? These are just the symbolic generators for the differential form algebra. So these are just symbolics. Whereas these d's, these are functions, these are smooth functions. These are partial derivatives of f. So these are smooth functions. So they are smooth functions defined on U. You can also write it a little bit differently. Some people would write, you can also say that df is, some people would write it like this. It's the partial derivative of f with respect to x1, where x1 just represents the first coordinate of the function, and then you multiply. So this is a smooth function, and then you multiply it by dx1, where dx1 is the differential symbol. And then you do it all the way up to the last one. This is the other way people write it. So this is the way you define this operator d. You take a smooth function, and this is the way you differentiate it. This is called the exterior derivative, and you can see you end up with a 1 form because these are of dimension, this is of degree 1, right? You have a single monomial for each one. So this entire expression is now a 1 form. So to show you an example, very simple example, let's say we have a function from R2 to R. Okay, so this is going to be a smooth function on R2, which is the same thing as just a 0 form on R2. And let's say the function is defined, let's write it as xy. Let's say the function is defined as e to the x squared y. Right, that's a nice smooth function. Then the exterior derivative of f is equal to, and this is by definition, this is how we define it. The exterior derivative of f is, you would take the partial derivative of f with respect to the first coordinate, then you just write dx, plus the partial derivative of f with respect to the second coordinate times dy. And if you work this out, so if we work this out, so that would be 2xy e to the x squared y plus, and if we differentiate it with respect to y, that would be x squared e to the x squared y. And then I forgot to write, of course, dx dy. And this entire piece is now an element of one forms defined on R2. So these are one forms, right? This is a one form, this is a one form, because you're only using a single differential now. And this is what we get. So that's the way you define it for zero forms. How do you define it more generally? So to define D more generally, and this is going to be from K forms to K plus 1 forms, it is sufficient to define D on monomials, i.e., we're going to assume that, so usually a differential form is denoted by a lowercase sigma. So we're going to pick a differential form in that set, which for us, it's going to look like this. So it's a monomial, and it's a monomial where you're choosing k of them. So it's going to go something like this: dxi1 wedge dxi2 wedge dxik. Okay, so you're just choosing k of these indices, and then you have an arbitrary smooth function in front, f. That's what I mean by a monomial. In general, a differential form will be more complicated. It would be a sum of monomials of this type. But because D is going to be defined in a linear way, you only have to define what it does to a single monomial. And then we define, then D omega is equal to, by definition, this is the way you find D omega. You just apply the differential operator to this function over here, right? You just differentiate that function, exterior derivative to that function. So you do df, like what we've done before, and then you keep everything exactly the same. Here you have to be careful about the order, because this algebra is anti-commutative. So you would have to be careful about in what order you write it, so you do not mess up the signs. But this, whatever this is now a one form. And this is a k form. So in total, the number of differentials you have, this is a k plus 1 form. And so we're getting something that now belongs to k plus 1 forms defined on U. And that's our differential operator, exterior derivative operator. It takes us from a k form to a k plus 1 form. So that's how it's defined. And now we have something very interesting that emerges out of this. So here's a proposition. The proposition is that d squared is equal to 0. And this should remind you, this is similar to the other proposition we've seen before, is that the boundary operator on chains, when we talked about homology, is equal to 0. And this is almost the same thing. So more specifically, this is what we mean. What we mean is that if you look at k forms go up to k plus 1 forms, and they come from k minus 1 forms. And we have d over here, and we have d over there. And we're saying that if you compose it twice, you get the 0 mapping. That's what we mean by d squared is equal to 0. And the proof of this is actually quite simple. So I'm going to give you a partial proof. This is going to be a partial proof that contains the main idea. The general proof is identical, but it gets messy with indices. So if you try to, when you generalize this proof, you're just going to see it's the exact same proof, you just have a lot of indices that you have to worry about. And it makes the proof look more complicated than it actually is. So I'm just going to show it to you in the simplest possible case, and you'll see that what's the idea that makes this work. So the special case So the special case is we're going to assume that U is an open subset of R2. It's because it's just going to make it easier because you're differentiating twice and you only have two different differentials. In general, if you do this with n variables, it's the same thing. It's just there's going to be just more indices. And you're going to let dx and dy generate the algebra, the differential form algebra on R2. I'm sorry, on U. So there's only two differential generators for this algebra. And we're going to also assume that our differential form is a zero form defined on U. So the differential form is just a smooth function, where f is a smooth function. And we're going to show that if you take the differential operator applied to omega and then you do it again, you end up getting 0. That's what we're going to show. So basically, we start with a 0 form. You apply the differential form operator. This is going to be a 1 form. And when you apply the differential form operator again, you're going to get a 2 form. But the 2 form is just going to end up being 0. So that's what we're going to show. So again, this is simplified. We're assuming we only have 2 dimensions, and then we're assuming we have a 0 form. But in general, you're just going to assume that you have n dimensions and that you have a k form. But other than that, the main proof, like the main idea behind the proof, is going to carry over to the special case. So the special case contains really the main idea that makes all of this work. So we compute df. So df, by definition, is we would differentiate f with respect to x times this differential, and then we would differentiate f with respect to y times this differential. And maybe for notational simplicity, let's just write this as fx dx plus fy dy, where f subscript x just indicates calculate the partial derivative function of f. And now we differentiate this again. We're doing it twice. So then df would be, you're going to apply the differential form operator on fx dx plus fy dy. What is this equal to? Well, by definition, this exterior derivative operator, it acts linearly. So you just distribute it on each piece, like this. And then what do you do next? Well, the next thing that you do is, the way d operates on the form is you operate d on the smooth function and you keep the differentials. That's the way it's defined. So by definition, this is going to be d applied to fx, and then you just wedge it with the differential. And then you do plus d applied to fy, wedged with the differential. And now we calculate what that is. So what is d applied to that function? So this would be wedge dx. Okay, so d applied to this one, you have to take the partial of fx with respect to x dx plus the partial of fx dy dy. Right? You're just applying the differential form operator on a smooth function, and then you do plus, and then you do the same thing with the other one. So this is what we end up getting, and then we wedge it with dy. And now we calculate this out. So we're taking the partial derivative in the x direction of fx. So we're just differentiating f in the x direction twice. So it's just fxx dx plus fxy dy. So we first differentiate x, then we differentiate y. Then we wedge this with dx plus, here we have fyx dx plus fyy dy, wedge dy. And now we can start computing this. So the way you multiply these differential symbols is, this is an algebra. So you basically treat them like polynomials, except it's anti-commutative. That's the only distinction. So you do dx wedge with dx. So you do fxx dx wedge with dx plus fxy dy wedge with dx plus fyx dx wedge with dy plus fyy dy wedge with dy. And then we said that if two differential symbols appear next to each other by the anti-commutative rule, that just cancels, and this one cancels. And so we're just left with fxy dy wedge dx plus fyx dx wedge dy. But look at this. These are repeated, but in the opposite order. So you can use the anti-commutative rule to write this as negative fxy dx wedge dy plus fyx dx wedge dy. And then this will simplify to be negative fxy plus fyx. And then we have dx wedge dy. So this is what we call combining like terms when you have a polynomial. So in a polynomial, the way you're used to, like in a polynomial algebra, you have like two indeterminates, two indeterminate symbols. Let's call them capital X and capital Y. And then you have capital, yeah, so maybe I should write it like this. So if this was a polynomial algebra, this would be like Y, that would be X. This would be X, that would be Y. But in a polynomial algebra, the way the indeterminates get multiplied together, it's that they're commutative, and then you combine like terms. So you will have xy, and then you have this one plus this one. So those are like combining like terms. But here, this is just an anti-commutative algebra, and so this is what you end up getting. But then this is, because these are equal to each other, this is what we call the mixed partials theorem. That when you have a smooth function, and it does not even have to be smooth, but when you have a smooth functions, there's a well-known theorem from calculus that says that the order in which you differentiate does not matter. The function in the end will be the same. And so this one and that one are really the same thing, so they cancel each other together. And this is really the main idea, right? So the proof, so what's the proof in general? So the proof in general is, this is just a fancy way of stating the claim that d squared is equal to 0 is just a fancy way of stating the mixed partials theorem. That's really what it comes down to. That we differentiate twice because of the d squared, and then we use the anti-commutative law to cancel the repeating mixed partials. That's basically what it comes down to. In the calculation that we just did, it's very easy to see because you only have two variables to deal with. But in general, if you do it with n variables, it would be the exact same kind of an argument, except the indices just become more complicated because there's like more indices to keep track of. But it's the exact same idea that you differentiate twice, and then you realize that one of the derivatives appears with a negative, and because they're equal to each other, they cancel, and that's why you end up getting 0. So this is what we end up with. So let's remove this and actually say something interesting out of this. So if U is an open Euclidean set, then we get what is known as a co-chain complex. So the co-chain complex, maybe we can say this is the co-chain differential form complex. And the complex is, you start with 0, so 0 just represents just the set containing 0, and then you can map that into 0 forms on U, and then you can map that into 1 forms on U, and then you can map that to 2 forms on U, and so on, by using the D operator on each of these. This one, of course, at the beginning, you just have to just artificially map it by 0 because you need to start somewhere, but the other ones, they just go up. This should remind you of the chain complex on a topological space when we get homology, but the boundary maps, they go down. The exterior derivative maps, they go up in degree. So we can define something called cohomology, which is exactly the same thing as homology, except it would go like this. You would use a superscript. So you would say the kth homology of an open set, and this by definition would be, you would look at the kernel of the map from sigma k of U to sigma k plus 1, and then you would mod out by the image of the previous one. So it'll be very similar, but we call this cohomology because it's just the chain complex that goes in a different direction. And we will talk about that at some point. Yeah, this is called the cohomology. The one thing that I want to say about cohomology is that these are actually, so these are actually vector spaces. All of these are vector spaces. Vector spaces over the real numbers. Well, they're actually both. So maybe I can say this. It's, so we've said this before, that omega k of u, this is a, you can say that this is a free module over the ring of smooth functions of rank n choose k. But you can also say that this is a vector space over the real numbers, because the real numbers are a special case of a smooth function, right? Every real number gives you a constant function, and a constant function is a smooth function. However, as a vector space, but this is an infinite dimensional space over the real numbers, right? There's an infinite number of smooth functions that you can consider. Like for instance, a very special type of smooth function is a polynomial function. And you have polynomial functions of arbitrary degree. So because of that, as a vector space over the real line, this will actually be an infinite dimensional vector space. But this is going to be a little bit reminiscent to when we talked about the chain complex. In the chain complex, we saw that when we talked about homology in the chain complex, these were free abelian groups with infinitely many generators. So this is kind of a little bit reminiscent to that as a module over smooth function, it will have finite rank, but as a vector space over the real numbers, this will actually have infinite dimensions. So it's like an infinite generated space over the real numbers. But when you take this quotient, you're actually going to be getting something that is more reasonable, something of smaller size. And what's going to end up happening is that these are vector spaces over the real numbers. That's what they are. You can also say that they are modules over smooth functions, but we primarily only concentrate them, and we generally just think of these as vector spaces over the real numbers. We get something that is a finite dimension in many cases, and there's methods for calculating that. So that's where we're going to be going with this. And also another thing that I want to say is this is done on Euclidean open sets, but we're going to generalize this. So very soon we're going to replace this by X, where X is a smooth manifold. And then instead of having an arbitrary open set in Euclidean space, we're just going to have a cochain complex on any smooth manifold. And then we can talk about the cohomology of that smooth manifold. So that's kind of where we're going with this. For those of you who might be interested, what is to follow next. But at least for now, we're just doing it for open sets first in Euclidean spaces before we generalize. The next thing we're going to define is we're going to define the induced morphism for differential forms. So this is what's going to happen. U will be an open subset in n-dimensional space, and V will be an open subset in m-dimensional space. They could come from different dimensions, it does not matter. And F from U to V is a smooth map. We know what it means for a map into R to be a smooth map. It means all of the partial derivatives of F exist, and you can differentiate as many times as you want. But when you're mapping it into V, and V is an open subset in Rm, then you really are mapping this into Rm. And to be a smooth map will simply mean then when you look at the component functions, these are the component functions are smooth. So that's sort of the obvious way to interpret that. That when it's a vector valued mapping, then each of the components of the vectors, you want them to be a smooth function on the components. Okay, so let's say we have a smooth map. This is a smooth map. Then F induces a map in the other direction. So we're going to call this F upper star, which goes from forms on V to forms on U. So it goes in the other direction. And this is going to be a linear map. A linear map in the other direction. So how does it get defined? So here's the way we define it. So to define F star, it is sufficient. Well, actually, before we do anything, we've seen something like this before. That if we have a differential form over here, the induced map, if you want the induced map to go in the same direction, we would, when we talked about, let's say, something like the induced map on homology or the induced map on the fundamental group, we do composition going like this. But if it gets swapped the other way around, we make the composition go the other way. So we want to write it like this. We want to be able to say, actually, sorry about that. We want to be able to say that F star applied to omega should be omega composed with F. We do the composition going the other way. The problem, of course, is what does that even mean? Because you see, a differential form is not actually a function. But it's kind of close to being a function because it's component, right? It's basically like a formal sum of differentials, but the coefficients happen to be smooth functions. So this idea kind of a little bit does make sense. But let's write it out explicitly how to do it. So here's the way we would do it, is we're going to assume that omega is a monomial. So we're going to think that omega is some function. Let's call this function g. And then we have a certain number of differentials. So here's what we're going to do. It's going to be convenient to tell these apart. So we're going to use different letters so that psychologically we can tell them apart. So the coordinates on U, let's call it x1 up to xn. And the coordinates on V, let's call it y1 up to ym. So the reason for doing this is because when we talk about differential forms on this one, it's going to be the algebra generated by the symbols dy1 to dym. And this algebra is going to be generated by the symbols from dx1 to dxn. Now, obviously, these are just symbolics, and they do not really mean much, but psychologically, it's convenient to be able to tell which one is referring to which one. So that's why we're using different letters so that we can sort of distinguish which one it is. And omega is going to be a monomial over here. This is going to be our monomial. So it's now this is a differential form on this one. So it'll be some function g, which is a smooth function on V, and you will have differentials over here. So you would have dy I1 wedge dy I2 wedge dy ik. So let's say it's a k form, and g is a smooth function defined on V. So then we sometimes call this the pullback of omega because it goes backwards. Omega is defined on this one, but f star over omega pulls it back, and it's now a differential form defined in that one. So how do we do it? Well, here's the way we do it. We're going to replace g by a composition. So g is a map. You see this g over here. It's a smooth map from V into R. And we have a smooth map from U into V. So we can replace it by a composition. So this is going to be F composed G, like this. And then what do we do with these ones? Well, what we do with these ones is we're going to look at the ith coordinate. You see, this f over here, it has m coordinates because it's going into y. It has m coordinates. So you're just going to take the ith coordinate of f. So this would be d of fi1. So this is d fi1 wedge df I2, df ik. So where fi1, this is the, well, maybe I should just write it like this, where f has been decomposed into coordinates. This is a smooth function with m components. So you just decompose it into components. These are smooth functions. And then you apply the differential operator to each of those component functions. Right? So this is the differential operator applied to a smooth function. So these are one forms. So this is a one form, this is a one form, and so on. So you have a wedge of k one form. So this is now a k form, and this is just a smooth function. And whatever you end up getting, so then f star of omega, this is now going to be a form defined on U. Because you have to understand, these are functions that are defined on U. So you're taking the exterior derivative of these functions, so these are individually one forms defined on U, and then you just multiply it by a smooth function on U, real valued smooth function on U, and then whatever this computation gives you, this is what you call the pullback of a form. Now, I want to just explain basically what you're doing. So this is the way it's defined formally. Okay, so this is the formal definition. But I'm going to show you a heuristic way of thinking about it. And I think it's best to just do it in an example. So I'm going to do an example. I'm going to do this example two different ways. I'm going to do it carefully in this way, and then I'm going to do it for you the heuristic. We often think of the heuristic when we do this. So let's look at this example. So here's an example. Let U be the, let's say the punctured, no. So let U be R2, let's say, and V represent the punctured. Yeah, so let's say U and V are both R2. Make it as simple as possible. And F is a function from U to V, and is going to be a smooth function. So usually what we do is the variables that we're using for U, we usually call them like x1 or x2, but I'm going to use like polar coordinate symbols. I'm going to call this r and theta, and for the other one, I'm going to call it x and y. So we're going to have f of r and theta, and that's going to be equal to, and then I have to map it over here. So with polar coordinates, I'm going to have r cosine theta, r sine theta, like this. Okay, so this is our mapping. This is a smooth function. These are smooth functions and all of that. And now let's make up an example of a one form. So now let omega be a form, a differential form defined on V. So for example, let's say this is the form that's, just to make something up, let's say it's the form that's given by minus x dy plus y dx. Okay, so this is a form, this is a one form, it's defined on V, and you can see that when we write our form, we write it in by using these variables. So if you want to be a little bit more specific, of course, these coefficients are referring to functions. So these are just going to be functions, these are smooth functions from V to R. And this is the function that takes the point x2, right? That's a point in V, and it just maps it to the first coordinate, to the negative of the first coordinate. So we just write it like this, but this is just a shorthand way of describing the function. So these are just functions, right? These are just, if it makes you feel better, you can write that this is f dy plus, well, maybe I should not call f, I'm already calling that f. So maybe I should call this like, let's say a dx plus b, a dy, b dx, where a is the function from V to R, and b is a function from V to R, and a is the function that takes x, y, and it assigns it to negative x and b is the function that takes x, y, and it assigns it to y. Okay, that's what those functions are, the coefficient functions, but it's just notationally more convenient to just write that. Now, here's the way we calculate the pullback. So the pullback, f star of omega, the way you do it is you compose. So this a over here, you're going to compose it with the f. So this is going to be a composed f. Okay, then you're going to have d, and as in the definition, the y is referring to the second component of your mapping. So it's going to be d of this function, right? This is r sine theta plus b compose f d r cosine theta. And if it makes you feel better, this is really just the first component, and this is the second component. This is the second component, and that is the first component. This is the second component because we have a dy over here. So you find the second component of your mapping f, of your smooth mapping f. This is a smooth function, and you're going to take the exterior derivative of whatever that function is. But it's just notationally simpler to just replace it by whatever that is. Okay? And you do the same thing over here. And now you get to calculate this. And by the way, this composition, f composed with f, so that would just mean that the a function, it gives you negative x. So when you're doing this composition, the function that you're getting is it's negative x, but this mapping, the x component is negative r cosine theta. So this one is really negative r cosine theta, and this one is going to be r sine theta, like that. That's what those compositions are. So the heuristic here, so this is the heuristic. The heuristic is just to replace you can say the new variables by the old variables. That's what we're doing. So in other words, this is what we call substitution. So to put it very simply, symbolically what we're doing is we have a differential form that's defined on V, and it's written in terms of symbolics x and y. But this mapping, you see, this mapping f, it takes you from r theta and it sends you to this. The first component, this is what x gets replaced by, and this is what y gets replaced by. So where you see the x, you're going to just replace it by negative r cosine theta. And when you see the y, you're just going to replace it by r sine theta. And then these differentials, this is d, and is going to be the differential of the y component function, which in this case would be r sine theta. And this is the differential applied to the x component function, which is this. So that's the heuristic. You're basically just replacing one set of variables by a next set of variables. And now when you do the calculation, you end up getting r cosine theta. And then the differential of this, now you apply the exterior differential operator to this form. This is now a function of two variables, where these are, so instead of calling it like x1 and x2, you're just calling it r and theta. That's the choice of the symbolics that you're using for the differential form algebra. So you would just differentiate this function with respect to the first variable, which in this case we're calling it r. So that would be sine theta. And then you write down dr plus, you differentiate it with respect to the second variable. So this will be r cosine theta d theta. And then you have plus r sine theta. And then you do the same thing with the other one. You would differentiate it with respect to the first variable. So we have cosine theta dr, and then we have minus r sine theta d theta when you do that. And what you end up getting is when you actually multiply this out and you simplify out, whatever this is going to be an element. This is now a one form on U. It's a one form on U. It's the pullback. It takes you from form over here to form over there. So now that's a one form on U. And when you're writing forms on U, you're going to be using the symbolics dr and d theta. So this is just going to be something in terms of dr and d theta. And this is basically how the pullback operation works. It's basically just substitution. So let's remove this, okay? And I want to write a proposition over here. So suppose U, V, and W are open Euclidean sets, possibly different dimensions. And say that we have f, a smooth function from u to v. We have another smooth function from v to w. And we have a smooth function from u to w called h. So f, g, h are smooth. And the diagram commutes. So then, anytime you have such a diagram, you have the induced map on the differential form algebra that goes in the other direction. Like this. So then this is a commutative diagram also. So that's what we're claiming. That this pullback operation, it's reminding us of a functor. It's some kind of functor in a way. So how do we prove this? Well, this is basically in disguise. This is basically the chain rule in disguise. So this fact is just the chain rule in disguise. It's hard to see it, but once you see it, then it makes sense. And I think it's just best to illustrate this in a very simple example. So for simplicity, let's say that u, v, and w were all one-dimensional Euclidean spaces. And even more simply, let's say they're all equal to R1. So we basically have this. We're going from, we have a smooth map from R to R called F. We have a smooth map from R to R called G. And then we have the composition H. And let's introduce coordinates so we can tell them apart. Let's call this X, let's call this Y, let's call this Z. So what happens when we look at when we apply the pullback? So when we apply the pullback, we go like this. And I want to show you that this diagram commutes. And I should say these are forms, right? These are going to be forms. This is going to be the form that's generated by the symbolic dz. This is going to be the form that's generated by the symbolic dy. And this is going to be the algebra that's generated by the symbolic dx. So let's see what happens. So to show that this diagram commutes, to show that the diagram commutes, let us show that dz, the generator, so it's enough to show it commutes on the generators, right? The generators are what matter. So you just have to show it commutes on the generator. So here there's only one generator, dz, to show that dz goes to the same thing, to the same form, along the two mappings. So we have to show that if you take dz, so if you start down here and you apply g star to it, and then you apply f star to that, that will give you the same thing as going this way. And you end up getting the same thing. So how do you do this? Well, here's basically the way that this works. How do you calculate on a heuristic level? How do you calculate, let's say, h star of dz? So you're saying that you're now thinking of z as a function of x. So you have to, you see, you have this mapping over here, and what you basically want to say is this is the derivative operator applied to h, because it's the z component. In this case, there's only one component because these are just one-dimensional spaces. It's just the first component, but it's how would you do that? Basically, what you're essentially saying is you're taking the derivative, the exterior derivative of f, but the heuristic here is this is just going to be you're going to differentiate z. I mean, the heuristic approach is z is written in terms of x. And how do you calculate the differential operator of this? You're going to differentiate z with respect to x, and then you write x. So all this means, like if you're confused by what this means, is you're just thinking of h as a mapping from this one to this one. And the way you calculate the pullback of this form is you would take the exterior derivative of h. How do you take the exterior derivative of h? You differentiate h with respect to that variable, but instead of writing dh dx, I'm writing it the heuristic way of dz dx, because I'm deliberately trying to indicate that I'm now thinking of z as depending on x. If maybe if this makes it a little bit easier, you're basically saying that this relationship over here is that z is equal to h of x. That's what you're basically saying, right? The z coordinate is equal to h of the x coordinate. So what we really are doing is we're just differentiating the h function, but symbolically it's more convenient to just write it like that. And the dx, that's just the generator for this algebra. Now, how do you calculate this one? Well, the way you calculate this one is you're saying that g, so you're saying that z depends on y. So here what you're saying is f star, and then this would be dy, I'm sorry, this would be dz, dy, dy. Because now this function, right, this function z depends on y by this function. So you're just writing this, but of course, what you really mean to say is you're differentiating the function g. And that's just dy. And when you pull this back again, you're going to, you have to pull this one back, right? You have to pull this one back. So when you pull back the dy, y is now a function of x. So you would end up getting here dz dy, and then you would write dy dx dx, and that's equal to dz dx dx. See, this is exactly the chain rule. That this piece is equal to that piece. If you want to write it maybe a little bit more carefully, this is the heuristic. If you want to write this maybe a little bit more carefully, then the way you would write this would be that this h, how do you get the pullback? Well, it's going to be written in terms of x. So it's going to be in terms of dx. That's our generator for this algebra, for this differential form algebra. But what do you do with the function? Well, the function gets differentiated. So that's just h prime. It's just h prime because it's just a function of a single variable. So you just differentiate that function that you have over here, and it's just dx. Now, what do you do with this one? This one will be f, the pullback of this g. It's going like this. So this would just be g prime dy. And then you want to do f star of this. Now, to do f star of that, you would do composition. Right? You would do composition. So you would do f. So this would become dx. So this will become dx. And then you would have g star composed f, because you have to put the function in here. So that's g star composed f. And then this function gets differentiated. So you would have f prime. And by the chain rule, this piece is exactly g composed f prime. dx is equal to h prime of x. And these are equal because h is exactly g composed f. Right? So these are now equal. So you can see that it leads, in the end, it just leads to the chain rule. So it really is just the chain rule in disguise. So when you do it in the single variable case, you get the usual chain rule that it is. In the multi-dimensional case, if these were of different dimensions, then you're just using what we call the multivariable chain rule in disguise. That's really what it is. Notation-wise, it's a bit annoying to work it out with all of the indices, but at the end, this is really the idea of what you're doing. You're essentially, the way these pullbacks work is they work by composition. So by substitution, you substitute, and then you substitute it again, right? You substitute it twice, and that's really what the chain rule is. So this is what we call the induced map on the differential form algebra. And it looks like a functor, right? So it's reasonable to ask, is the differential form algebra a functor? And the answer is yes, but it is hard to say what the category is. So it happens to be a functor from smooth manifolds. And so this one we kind of understand. It acts on smooth manifolds. But what do we put? So this is a little bit unclear. Here you need to learn about these things called sheaves and so on, which I do not want to go there because that's just not necessary for us. Sheaves is an idea from for the most part, in algebraic geometry. They're very complicated, very abstract, and we just do not really need to know that. So it is a functor, but I just do not want to say what the category is because that will take a lot of work to actually define what that category is, and we just do not need that. The most important thing you want to get out of this is that if you have two Euclidean open sets, you get an induced map the other way on differential forms. And in fact, you can even specialize. You can say that if you have a K form, it goes to a K form. But in general, it goes from a differential form to a differential form. So that's like a summary of what this is. This is what we call the differential form functor, though we're not saying what the actual category is. So so let's just say this. All right, this class, right? So this lecture has introduced differential forms on Euclidean open sets. So next time we will generalize and define differential forms on smooth manifolds. Anytime you have a smooth manifold, you can talk about differential forms. Euclidean open sets is a special case of a smooth manifold because Rn, this is a smooth manifold with the obvious atlas, and U, this is an open subset. And you had a question on the homework that said that anytime you have a smooth manifold, then an open subset of that manifold is also a smooth manifold. So this is, of course, a special case of something that's a lot more general. But we really want to get to the way you do it on smooth manifolds. And you kind of do it in two steps. You first define it in the Euclidean way, and then you can generalize that to smooth manifolds because basically a smooth manifold is a collection of charts, right? It's what we call an atlas, a collection of charts. And the charts are defined on Euclidean spaces. So a smooth manifold, you have charts, and the charts themselves are done on Euclidean spaces. So that's kind of the reason why we first do it in Euclidean spaces, and then we will generalize it to an arbitrary smooth manifold. So this is where we're going with this. And like I said, I understand that these definitions are not very motivating. It's not clear why we want this. But later on, we will see the benefit, right? The real reason for why we care about differential forms. At the moment, it's not very clear, but basically, differential forms are invariant under coordinates. And you will see what that means when we get to integration. Basically, when you have a smooth manifold, you have some kind of smooth manifold, and you have a piece of the manifold, then that piece of the manifold can come from one chart, or it might come from a different chart. And when you do a computation in a chart, we want to make sure that the answers are always going to be consistent no matter how you do it. And that's exactly what differential forms will do for you. They will enable you to do, one can say, calculations and coordinates in a way that's safe, where regardless of what chart you use, you will always end up getting the same answer. And that's the real reason why we care about differential forms, because manifolds, they are chart dependent, right? It's just made out of lots of charts, and you want an object that remains invariant that you do it. So that's like the big idea for what differential forms do. But I think it's more helpful to just learn the algebra of differential forms first and get comfortable with that before we explain more carefully what we mean invariant under coordinates.